guys, so let's start our review with one-dimensional kinematics. So we started this section talking about motion, and to talk about motion we had to talk about position. We defined displacement as the change in an object's position calculated by a straight line measuring the length between the final position and the initial. So our first equation is delta x, which represents displacement, is equal to position final minus position initial. Now recall that displacement is not the same as distance, and in the figure here in the notes, the displacement is indicated by the orange line and the distance is indicated by the teal squiggly line. So then once we talked about position and displacement, we could talk about how quickly the position changes, or the rate at which the displacement changes, and that quantity we called velocity. So our formula for velocity is delta x over delta t, and remember that this is an average value of the velocity. An object that is accelerating to a certain final velocity is not going at the same speed the entire time. And so when we calculate delta x over delta t, we're really getting an average. If you were to calculate the instantaneous velocity at a particular time t, then you would need to calculate the slope at that point. So you see here in the diagram, if we had this graph of velocity, then we would need to calculate the slope at a particular time. So if we're looking at instantaneous velocity here at time t, we need to calculate the slope at that point. Then once we talked about velocity, we began to talk about the rate at which velocity changes, which we called acceleration. And we calculated the average acceleration as being delta v over delta t. And remember, anytime you see delta, that means final minus initial. For an object that's moving with a constant acceleration, the average velocity is simply v initial plus v final divided by 2. Then we took a look at the graphical representation of these values. So we saw a position versus time graph where the slope on this graph was equal to velocity. Any points below the t-axis means that the position of the object is in the negative direction, but remember that the object could be heading towards the zero or away from it depending on the slope or depending on the sign of the velocity. And conversely, for above the t-axis, then the position of the object was in the positive direction, and the object could be moving either towards the zero or away from it depending on the slope or depending on the sign of the velocity. Then we saw velocity versus time graphs where the slope of this graph was equal to the acceleration. The area under the curve of the velocity graph is equal to the displacement. And when you are below the t-axis, it means that you are heading in the negative direction. And when you are above the t-axis, you're heading in the positive direction. So if I was to give you a verbal description of this orange graph right here, I would say this object starts with a negative velocity and continues in the negative direction, but the object is slowing down, meaning the magnitude of the velocity is decreasing until the object stops. When the object stops, that's this point right here where the graph is passing through zero. So that's where velocity equals 0. And the object changes direction because after this point, now all of the velocity points or all the y values are above the t-axis. So the object changes direction, and then it's now moving in the positive direction and speeding up. Okay, so then we saw acceleration versus time graphs, and we haven't seen anything other than linear acceleration graphs. So remember that the area under the curve of the acceleration graph is equal to velocity. And the way that you would plot your points on the acceleration graph is by plotting the slope on the velocity graph. So if you look at the velocity graph, I've written in blue the trend of the graph, of the slope. So the slope starts at 0 and it becomes increasingly positive. So your acceleration graph would resultingly start, I'll draw it in a different color here, would start at 0 and get increasingly positive. So that would be the acceleration graph of the velocity graph pictured above. Then we applied this one-dimensional kinematic concept to freely falling objects, so objects in free fall. Remember that two objects dropped from the same height will hit the ground at the same time, and that's because the time in the air depends on delta y, not on the mass. So if you dropped a bowling ball and a bag of feathers from the same height, they would both hit the ground at the same time. In free fall, acceleration is constant whether the object is moving up or down, and that acceleration is always equal to g, or gravity. At the top of this motion, if something is thrown up and then falls back down, at the very top here, velocity is 0 because that's where the object is changing direction. For a dropped object, we would see this velocity graph right here. Okay, for a dropped object, so that means starting at rest. So VI would be 0, and you see that the velocity increases at a constant rate, and that rate is equal to gravity. And here for a ball that is thrown in the air, we start with a greater velocity, right? Greater velocity right when the ball leaves the hand, and then a velocity of 0 at the peak of motion, and then the object would change direction and increase its velocity again in the opposite direction. Okay, so here's our review question written with a little more clarity. So let's go ahead and solve this one. So here we are, 2 meters above the floor. A volleyball is hit straight up. V initial is 6 meters per second. I know here at the peak, VF is 0 meters per second. The ball falls back down to the floor, and we want to know what is the total T. So the first equation that I'm going to start with is VF equals VI plus AT. So I'm going to look at just half of the path of the ball, meaning from the time it's released to the peak where VF is 0. Okay, so the peak of the trajectory. So I'm going to solve first in variables. So I get VF minus VI equals AT divided by A, and I get T equals VF minus VI over A. VF is 0 meters per second. VI, I made up positive and down negative. VI is positive 6.0 meters per second, and A is negative 10 meters per second squared. So that gives me 0.6 seconds. So from the time the ball is released to the peak here, okay, this takes 0.6 seconds. Which means from the peak back down to the initial starting point also takes 0.6 seconds, at which time the velocity here is negative 6 meters per second. So I know that the total time for the ball to start 2 meters above the ground and to reach the point symmetrically that is also 2 meters above the ground on its way back down is going to be 0.6 seconds plus 0.6 seconds, or 1.2 seconds. Okay, so that's the time for the ball to start 2 meters above the ground, reach the peak, and then come back down to its initial height above the ground. But now we also want to know how long it takes the ball to fall those 2 meters. So we can use another equation. I'm going to use this equation, and I'm still going to look at the first part of the path of the ball, meaning from the time it's let go to the peak, so I can still use 0 as my V sub f, and I'm going to find out what was the change in position of the ball from its point 2 meters above the ground to its peak. So I'm solving for delta x. So VF squared minus VI squared divided by 2a equals delta x, or 0 meters per second squared minus positive 6 meters per second squared divided by 2 times negative 10 meters per second squared. So we have a negative 36 divided by negative 20. And that gives me 1.8 meters. So now I've just solved for the distance that the ball travels before it reaches its peak and changes direction. So the time that the distance that the ball covers on its way back down would be the 1.8 meters plus the 2.0 meters. So utilizing, if we go back to our notes, utilizing this equation here, that leaves out v sub f. So I'm looking at the second equation of delta x equals vit plus 1/2 at squared. If I utilize that equation, and I'm looking at the path of the ball from its peak to the floor, where this is a distance of 1.8 meters plus 2.0 meters, Vi is 0, A is negative 10 meters per second squared, then I can solve for my time. So let's solve for t. We know that v sub I is 0, so this term cancels out. And we can multiply both sides by 2, so we get 2 delta x equals at squared divided by a. T squared equals 2 delta x over a, and we'll square root that. And t equals the square root of 2 delta x over a. And actually that 3.8 is negative because we're moving towards the floor. Okay, so let's see what we get. 2 times 3.8. So we get t for the path of the ball from its peak back down is 0.87 seconds. And so I apologize up here at the top where I said that the ball, the time it takes for the ball to reach its peak and then reach the corresponding point on its way back down 2 meters above the floor is 1.2 seconds. We actually don't need that. I apologize. So we just need the 0.6 seconds from the release to the peak, and then from the peak to the floor, 0.87 seconds. So we get 0.87 seconds plus 0.6 seconds, 1.47 seconds. That is the total time that it takes for the ball to hit the floor. Okay, so let's continue with the last practice question. So Dustin accelerates his car from rest at a rate of 8 meters per second squared. So this one is giving us the acceleration. So we have Vi is equal to 0. Remember, starts at rest means initial velocity is 0. A equals 8 meters per second squared. What is the displacement of the car in the first 10 seconds? So it's giving us a t equal to 10 seconds, and we're solving for delta x. So the variable that we are leaving out is final velocity. So we're going to use the second equation. So we're using delta x equals VIT plus 1/2 AT squared, and it's already solved in terms of delta x, so that's great. We'll just plug in values. So we get 0 times 10 seconds, so that term goes to 0, plus 1/2 times 8 meters per second squared times 10 seconds squared. Don't forget that squared, people. A lot of you wrote the squared in and then didn't calculate it. So 0.5 times 8 times 100. So 400 meters. How fast is the car moving after the first 10 seconds? So we have a t of 10 seconds. We still have vi of 0, a of 8 meters per second squared. This time we're looking for vf, so we can leave out delta x. So let's use the first equation. Vf equals vi plus at, where vi is 0, 8 meters per second squared times 10 seconds, or 80 meters per second. And everyone's favorite question, the chicken spotted ahead down the road. So Dustin's driving at a speed of 25 meters per second and he sees a chicken 108 meters ahead. He takes 0.8 seconds to react. He hits the brakes and accelerates at negative 3.45 meters per second squared. How far has he gone when he stops, and does he hit the chicken? So first let's calculate the delta x of reaction. Okay, so Dustin takes 0.8 seconds to react, which means that he is driving at his constant speed of 25 meters per second for 0.8 seconds. So 25 meters per second times 0.8 seconds is 20 meters. So he goes 20 meters before he even presses on his brakes. Then he hits the brakes and accelerates at negative 3.45 meters per second squared. Okay, so his VI, 25 meters per second. VF, because we want him to stop, is 0. Acceleration, negative 3.45 meters per second squared. We are solving for delta x. And so we could leave out time. Okay, so we want to use the last equation here. So we'll use VF squared equals VI squared plus 2A delta x, where we're solving for delta x. Delta x equals VF squared minus VI squared divided by 2A. VF squared is 0. VI squared is 25 squared. So 625. I'm wondering if you guys can hear my parrots being crazy in the background. I apologize. The acceleration, negative 3.45 meters per second squared. So let's see, negative 625 divided by 2 times negative 3.45. That gives us 90.58 meters. So it takes him 20 meters before he presses on his brakes, and then he goes another 90.58 meters to stop. So total delta x, 90 meters. Apologize, 90.58 meters plus 20 meters. 110.58 meters. No, he hits the chicken because that distance is greater than the chicken's position, which was 108 meters ahead of Dustin. So Dustin hits the chicken.